Welcome back to the deep dive. If you've been following the world of AI, you know that language models are evolving quickly. I mean, they're moving past just generating text to actually doing things.
That's right.
And today, we're not looking at some gargantuan 100 billion parameter model. We're focusing on a real breakthrough in compact, efficient AI that can interact with your computer screen. Well, kind of like a human.
We are deep diving into Fara-7B. It's the newest agentic model out of Microsoft Research, and it's just a fascinating study in design efficiency. They've engineered a model with just 7 billion parameters, which is, tiny by today's standards, to automate genuinely complex web tasks.
So our mission today is to really unpack the whole system. We need to get into the architectural design choices for Fara-7B, and maybe even more importantly, that revolutionary data pipeline that lets this small model achieve state-of-the-art performance on what the researchers call computer use agent tasks, or CUA tasks.
And defining that technology is really key here. Fara-7B is an agentic SLM, a small language model, and it's specialized for those CUA tasks.
Okay, so what does that mean in practice?
It's a crucial distinction. It means it's built to actually operate the interface. It uses simulated mouse inputs, keyboard actions to achieve real goals.
Like finding the cheapest flight or filling out a multi-step form online?
Exactly. And what immediately jumps out from the sources, and we have to talk about this first, is just the sheer efficiency.
The size, right, 7 billion parameters.
Right, it's ultra compact. But the papers show it's completely competitive with much larger, more resource-intensive systems. I mean, those bigger systems often have to chain together multiple colossal models just to finish one task.
So that leads us right into what you called the 7 billion paradox. Why is being small not just a nice-to-have, but actually critical in this domain?
Well, when you think about these CUA tasks, you're thinking about high-frequency interaction.
Dozens of decisions a minute, maybe.
For sure. And if you have any latency, it just kills the user experience. So the implications of that small size, they all center on deployment locality. Fara-7B is explicitly optimized to run directly on your device, specifically in the Copilot plus PC environment on Windows 11.
So because the model is small, you don't have that constant round trip to the cloud for every single little action it wants to take.
Exactly. And that reduction in latency, for the user, it must feel instantaneous. Instead of that network lag, the decision is just processed right there by the device's hardware.
The speed is a massive factor, but for the user, what about security, privacy?
That's arguably even more profound. I mean, think about it. If the agent is automating personal tasks, like logging into your bank or booking a flight, all that context, the screenshots, your action history, it all stays local.
It never leaves the device.
Never. So this design choice, it directly supports that vision of personal and private agentic computing that they talk about in the paper. The agent really does function like an integrated assistant, but without the privacy trade-offs.
And it all ties into the hardware, leveraging the on-device NPU acceleration that we're seeing in modern silicon.
Precisely. And the best part, to really encourage development here, Fara-7B is an open-weight experimental release. It's under an MIT license on Microsoft Foundry and Hugging Face.
So developers can start playing with this on-device CUA tech right now.
The barrier to entry is incredibly low.
Okay, let's unpack the core mechanism here. How does Fara-7B actually interact with a computer? Most of the successful agents we've seen before needed two things: the visual screenshot and the underlying code of the web page, the accessibility tree, or ACS tree.
Right.
Does Fara-7B use that?
No. And this is where its architectural simplicity is just brilliant.
Yeah.
Fara-7B works entirely by visually perceiving a web page. It only processes the browser screenshot, and from that, it directly predicts the coordinates for its actions.
So it operates just like a human user would just by looking at the screen.
Just by looking.
Let's pause on that because that's a huge engineering decision. For anyone who's not familiar, what exactly is an ACS tree, and why is getting rid of it such a big deal for efficiency?
So an ACS tree is basically a structured, non-visual skeleton of the web page. It's got details on every element. Is it a button, a text field, a link, and what its role is?
Okay, so it's like the blueprint.
It's the blueprint.
Yeah.
And older agentic systems had to process this tree structure with one model to understand the page semantically, then process the screenshot visually with another, and then try to sort of align those two streams. It's complicated.
Reading the blueprint while also looking at the finished building?
A perfect analogy. Fara-7B just looks at the building. It skips the blueprint altogether. It doesn't need separate models to parse that structural data.
Which drastically simplifies the input pipeline.
Massively. Less data needs to be processed for every single decision, which is absolutely vital for speed.
That right there answers why a 7B model can be so fast. It's not just smaller, it has a much more streamlined input. So when it makes a prediction, what context is it actually looking at?
Okay, so for every single step, the model gets all the user messages from the start of the task, the complete action history, so the clicked or typed so far, and the latest 3 screenshots of the browser window.
3 screenshots. And I guess the long context of the base model is what makes that possible.
It's critical for maintaining that history across these long, multi-step tasks.
And the output. It can't just be a set of coordinates. It has to be a full action.
It's a very strictly formatted output. First, it outputs a reasoning message. This is kind of like the agent thinking aloud about what to do next.
Okay.
And that's followed by a structured tool call. These are things like a very precise click XY on predicted coordinates or type text XY. It also handles macro actions, web search or visitor role.
And the paper credits the base model choice for making this visual-only approach work so well. Which one did they use?
They built Fara-7B on Qwen 2.5 VL7B. It was a really strategic choice. That model is known for being great at grounding tasks.
Grounding, meaning visually locating and interacting with things.
Exactly. And it also supports these incredibly long context windows, up to 128,000 tokens, which ensures that action history doesn't just get lost in a complex task.
Neural signal check. Here's why this development actually matters at a deep level. We know the model architecture is important, but for any agentic system, the real bottleneck is usually the training data.
Always.
And the sources are really clear. Collecting high-quality, human-annotated computer interaction data is just prohibitively expensive. So what was the engineering solution to get data at scale?
This is really the core innovation story of Fara-7B. They relied on a novel, fully synthetic data generation pipeline built on top of the Agentic 1 framework.
So instead of paying thousands of people,
They automated the whole process. They built an AI system to create the training data for another AI system.
that's a very advanced way to create data. Let's walk through the 3 main stages of this process. It's detailed in Figure 2 of the paper.
Okay, so the pipeline starts with task proposal. The goal here is just diversity and relevance. They generated thousands of synthetic tasks like find me a blue sweater on sale or book a flight from Seattle to New York.
And how did they make sure those tasks were realistic?
They were seeded by a web index of public URLs, shopping sites, travel portals, you name it. And then a refinement LLM agent would actually explore the website to make sure the task was even solvable. This process created a whole new benchmark they call Webtail Bench.
So task proposal gives you diverse, realistic inputs. What happens next when the system actually tries to solve the task?
That's stage 2, task solving. And this uses a specialized multi-agent system built on Agentic 1. It's highly orchestrated.
More than one agent.
Oh yeah, you have an orchestrator agent for high-level planning, a web surfer agent that turns those plans into actual browser actions, and even a user simulator agent that can step in if the task needs some back-and-forth conversation.
And this system generates a trajectory, a full record of observations, actions, and even the agent's thoughts.
Right, that trajectory is the gold standard training data. But with synthetic data, you always have to worry about quality control.
Of course. If the solver agents mess up, Fara-7B is just going to learn those same mistakes. How do they check the quality?
That's the crucial third stage, trajectory verification. They deploy 3 separate verifier agents to evaluate if the task was a success. It's a really rigorous check.
3 different verifiers, what do they each do?
The first is the alignment verifier. It just checks if the final result matches the original task's intent. Then you have the rubric verifier, which scores the performance against specific criteria like, did the shopping cart actually contain the right item?
Okay, so intent and correctness. What's the third one?
The third is the multimodal verifier, and this one is critical. It confirms that the visual evidence in the screenshots actually supports the claim that the task was completed successfully. Only the trajectories that pass all 3 of these checks are used for training.
Wow. That multi-agent approach sounds incredibly complex, but the goal is to distill all of that down to train a single 7B model.
And they do it using a very standard approach, supervised fine-tuning.
Which is a staggering simplification, really. The complexity of that whole solving system gets linearized, just flattened into a simple observe, think, act sequence.
Right, and it's perfect for training the single Fara-7B model using a standard supervised fine-tuning loss, or SFT.
Why is relying only on SFT a breakthrough here? Agentic systems so often need really deep, resource-intensive reinforcement learning, RL, to work in the real world.
RL is powerful, for sure, but it's notorious for being unstable and incredibly complex and expensive, especially for something like web navigation.
Hmm.
By creating such a high-quality verified synthetic data set, the researchers proved that SFT alone, which is way simpler, cheaper, and more stable, can effectively distill the behavior of that complex multi-agent solver into a compact single agent.
So they got these state-of-the-art results without all the instability that comes with RL.
Exactly. It's a fundamental finding, really. Data quality can absolutely trump the complexity of your training method.
So what was the final scale of this training data set?
They ended up with 145,000 trajectories, which is a massive 1 million steps of interaction. And this covered a huge variety of websites and difficulty levels, plus all those auxiliary tasks for the visual, side grounding, captioning, VQA, to make sure the model really understood what it was seeing.
Okay, let's move to performance because the numbers are what validate all these design choices. How does this compact visual model actually stack up against bigger competitors on benchmarks like Web Voyager or their new Webtail bench?
The results really establish Fara-7B as a clear leader in its size class. On Web Voyager, which is sort of the industry standard, Fara-7B hit a 73.5% success rate.
And let's put that in context. That's a huge leap over previous heavyweights.
It is. It compares very favorably to the big SOM agent, which is usually based on something huge like GPT-4o that scored 65.1%. And it even beats the previous 7B state-of-the-art model, UI-TARS, which was at 66.4%.
So small agents really can punch above their weight if they're designed correctly.
Absolutely. And just as importantly, Fara-7B got top performance on their new real-world-focused Webtail bench, hitting 38.4%. The sources emphasize that this benchmark has the hardest, trickiest, most generalized real-world tasks.
Like comparing prices across two different websites or something like that.
Exactly. Things that require real generalization.
Okay, beyond just accuracy, let's talk operational efficiency. Figure 1 in the sources plots accuracy against cost. How do they measure that?
Cost is basically computed on token usage. You multiply the average input and output tokens by the price per token. So it's a direct reflection of the cost and complexity of the model's decision-making.
And the findings there are pretty staggering, right?
They really are. Fara-7B is shown to be far more efficient because it's just more decisive. It completes tasks using only about 16 steps on average.
16 steps. And what was the comparison?
Its predecessor, UI-TARS, needed around 41 steps.
16 versus 41, that's a remarkable difference. In terms of real-world latency, that's not just a small improvement. That's the difference between a task taking 3 seconds versus maybe 10 seconds.
Exactly. It establishes a new Pareto frontier for on-device agents, where speed and accuracy finally converge. Fewer steps means lower latency, lower token cost, and less energy used by the NPU. It's a breakthrough across the board.
Before we wrap up the mechanism, let's touch on safety. It's framed as an architectural requirement. What's the mechanical safeguard they built in during training?
The training pipeline specifically forces Fara-7B to recognize and stop at what they call critical points.
And a critical point is what exactly?
From an implementation perspective, it's any situation that would require sharing the user's personal information or any irreversible action, like a financial transaction or submitting a legal form.
So the model is trained to recognize visually and contextually that it's reached a point where a human needs to give consent.
Yes. It ensures user control is non-negotiable. It's a really smart way to integrate oversight directly into the model's core abilities instead of bolting on some slow external monitor. The agent knows when to stop and ask for help.
That's a robust framework. So for the developers out there, how can they get their hands on this? Where is it available?
Like we said, Fara-7B is open weight on Hugging Face. It's also integrated with a research prototype called Agentic UI, so people can start building with it right away.
And for those working on on-device AI,
There's a specialized, quantized, and silicon-optimized version available for Copilot Plus PCs through the AI Toolkit in VS Code. So you can run it locally and take full advantage of NPU hardware acceleration.
that's true, immediate applicability. So looking ahead, what does the research say is next for these CUA models? Where do they go from this SFT-only success?
The researchers see it evolving in two main directions. First, just continuing to use better multimodal-based models will naturally improve the visual perception and grounding.
Makes sense.
And second, while they achieve state-of-the-art without it, the future will almost certainly incorporate reinforcement learning on live and sandboxed environments.
So using SFT to give the model its foundational competence and then using RL to fine-tune its performance in messy real-world settings.
Exactly that. That blend, SFT for stability and competence, RL for adaptation, that's what they predict, will lead to even stronger on-device CUA models with unprecedented reliability.
This has been a really profound deep dive.
Hmm.
Fara-7B really proves that these small, single-agent models with smart data engineering can distill the complex abilities of huge multi-agent systems.
Mm-hmm.
It's achieving SOTA results with just supervised fine-tuning, and it's setting a whole new bar for efficient on-device agentic computing, all by just looking at the screen.
It's a real affirmation that in AI, architectural simplicity and data quality can often beat sheer model size and complexity.
Yeah.
The ability to just throw away structural data like axe trees without a performance hit is a massive step forward for speed.
Okay, so a final provocative thought for you to consider as you explore this research. Fara-7B relies purely on visual perception, the screenshots, and its action history. And this is great for static websites. But how will researchers architecturally deal with scenarios where the crucial information is non-visual?
What do you mean?
Well, think about managing complex session state or handling sophisticated asynchronous browser events like a pop-up window that's loading data in the background. That stuff isn't immediately visible in the captured images.
That's a great question. It probably means you have to ask whether the context window needs to be augmented, not just with past actions, but with some kind of inferred session data or a state vector. That's the next frontier for these models, especially on the highly dynamic web applications we use every day.
Food for thought. Thank you for joining us for this deep dive into Fara-7B. Be sure to check out the source materials linked on our webpage to explore this groundbreaking research for yourself.